Well, good afternoon. Yours truly, Dolphy Gilpin is here with you again at 1524 LaVista Drive, second floor closet. We're applying some aircraft dynamics in closed confined spaces, synonymous to pilots and astronauts having to work in closed confined spaces like their cabins. In the cockpit's cabin, they are closed off with the passengers in the rest of the body of the airplane. Now we're going to deviate a little bit from our AMZ5X12M matrix and break down derivative matrices into some conventional or traditional linear representation for this aircraft dynamics, and then we are going to move back to develop the metrical form of it. So first we're going to start off in the linear form, and then we're going to formulate the matrices or the metrical forms. So we're on aircraft dynamics in closed confined space. Now we're working. And we now can develop good approximation of key aircraft phogoid using simple balance between kinetic and potential energy. Now let's consider now an aircraft in steady level flight with speed, initial longitudinal speed u sub 0, and height h sub 0. Initial height, h sub 0. The motion is perturbed slightly, so we have a slight perturbation. It's right here now. Slight perturbation. So such that now this initial longitudinal velocity tends now to u, which is now equal now to u 0 plus this small perturbation value. Similarly, this h initial now tends to now h, which is now equal now to h sub 0 plus delta h. Now if we assume now that the energy, kinetic energy now, is equal now to 1/2 m u square plus potential energy now m gh. And if you assume that this energy is constant before and after the perturbation, it then follows that now that u now is approximately equal now to g delta h over u 0. Yeah, that if we assume now that the energy is constant before and after the small perturbation, it follows that u is approximately now equal to g delta h over u 0. And from Newton's laws, we know that the vertical direction m rate of change of height now m dot h is now equal now to L minus W. W represents the vertical velocity. Where W is equal to mg, so you know that W is equal to mg, that is the mass times the gravity. And L is equal now to 1/2 rho S, which is now the wing area of the airplane, C sub L u square, which is the initial longitudinal velocity. We can then derive the equation of motion of the aircraft. So we have now that mh dot is equal now to L minus W is equal now to 1/2 rho wing area of the airplane CL into now u square minus initial u sub 0 square. And that in turn is equal now to 1/2 rho wing area of the airplane C sub L into u0 plus u square minus u0 square. And this is now approximately equal now to 1/2 rho wing area of the airplane C sub L into 2 now u initial velocity u. And so we have it now approximately equal to minus now rho wing area of the airplane into now G delta H over u sub 0, which is the initial longitudinal velocity, times u0. And my pen is really going on too. Let's try another pen. Oh, this is blue. And that's equal now to rho wing area of airplane C sub L gravity times now delta height. Now since the rate of change of height now, since h dot is equal to delta rate of change of height, and for the original equilibrium flight condition, L is equal to W, which is equal now to 1/2 rho wing area of airplane C sub L into now u square sub 0, which is now equal to mg. Mg is equal to W, which is over here. We get now that rho wing area of airplane C sub L gravity over mass will be equal now to 2 into G. This is going from the linearized representation, and we will develop the metrical representation from the linear representation into our 5/12. So we're going from our amazing 5/12 and its derivative to linear, and from linear into amazing 5/12 matrix and derivative format. So that's G into now u sub 0 squared. Now combine these results to obtain now that delta H, rate of change of height, plus now omega, and we'll have to come back and define some of these terms once more, because I'm hearing murmuring about a lot of parameters being used here and with no explanation, and that's equal to 0. So that omega is approximately now equal to G over U sub 0 square root of 2. And these equations now describe an oscillation called the phugoid oscillation. So all these equations now describe what you call the phugoid oscillation. Of the altitude of the aircraft. Of the altitude, the altitude H, of the aircraft and its nominal value. So we're going to stop here and we're going to continue with our aircraft dynamics in its linearized representation, and we're going to move to develop our derivative lowercase matrices, and which is a representation of our derivatives of the AMZ5X12M matrix representation. So let's take a break here from our aircraft dynamics being applied in confined spaces, and here significantly in the closet at 2nd floor, 1524 LaVista Drive, Decatur, Georgia, United States of America. Let's take a break and we'll return with some more aircraft dynamics.